17 in our vectors topic. If you haven't seen them, I would suggest you check them out first. This is example 18. So in this video, we're going to have a look at finding the angle between a line in space and a plane. So in the previous examples, we've had a look at extracting the kind of key direction information. And when it comes to two lines, we are extracting the direction vectors. So if we've got two lines in space, we're really looking at matching up or making an angle out of the two direction vectors, because they define the direction of each line. So if we work out the angle between them, then we're good. When it comes to two planes, well, we are in a situation where they'll usually intersect on a line. So if we've got a plane like that and a plane like that, remember that we're not so much interested in the direction of the plane as to the normal of the plane. The normal is at right angles to each one, and therefore we're going to end up with kind of two normal vectors going perpendicular to the plane, and they're the ones that we actually bring together to find the angle between. So what we're doing is we are focusing on where the direction information is. So in two lines, we take the two direction vectors. Two planes, we take the two normal vectors. But what happens when we're dealing with one of each? Okay, well, the diagram here will help us, because we've got our line L, which intersects the plane right down here at this point. Now, the information we'll have about a line, of course, is the direction vector, okay, which in this case is indicated by B. Okay, so we'll have some information about the direction vector of the line, but we'll also have information about the normal vector of the plane. So in actual fact, what we've got is we've got a line which goes in the direction of the line, and so we'll call that D. And we've got a line which goes in the normal to the plane, which we'll call N. So we can work out where those, or the angle of the intersection of those two vectors. So we're going to work out the angle of intersection here, but of course that's not the angle of intersection of the line and the plane. That is the angle of intersection between the two vectors. But what we do know is that the angle from the normal to the plane is, of course, right angled. So if we think about this, if we're kind of thinking about it in two-dimensional situation, we know that the normal has to be at right angles to the plane. So whatever we work out as theta, the difference to it is just going to be 90 minus theta. So we can work out the angle between the direction vector and the normal vector, but then we have to do one little small calculation to say the actual angle that we're looking for, which on this diagram is here. This angle here is 90 degrees minus this angle here. Okay, so we'll do it as an example. So example 18, find the angle between a particular line and a plane. So as we've always done, we'll extract the kind of direction information. For the line, we can say that the direction vector, we don't need D1, we've just got 1. So we can say from the line, we can say the direction vector is 4, 3, 2. And from the plane, we can say that the normal vector is 10, negative 2, and 1. Okay. 10, negative 2, and 1. So we can work out an angle for sure, but remember, I'm just going to put angle between the line and the normal, not the plane. That angle is, so we can say cos theta equals d dot n, the scalar product of the two, divided by the product of their magnitudes, which we just go ahead and do. Scalar product DNN 4, 3, 2, 10, negative 2, 1, 40, minus 6, plus 2. What does that give us? 34, 36. We've got 36 on the numerator, and we're going to work out the two magnitudes. That's what we've got. The magnitude of D is the square root of 4 squared plus 3 squared plus 2 squared. That gives us 16 and 9 and 4, which is square root 29, which I'm going to leave as square root 29 because I'm going to use a calculator later on anyway. The magnitude of the normal vector is the square root of all the components of the normal vector. Which would be the square root of 105. So we can put those two numbers into our angle calculation. Root 29 times the square root of 105, and if I do that in my calculator, I'm going to end up with 0.652. That's the cos of the angle. Let's bring this up a little bit. Which means that the inverse cos of 0.652 is 49.3 degrees. Okay, what is that? That's the angle between the line and the normal vector. So what we need to do, so just a wee reminder, is that here's our normal vector, here's the plane, and what we worked out is that the line makes an angle of 49.3 degrees with the normal, which means that we're looking for the complement of 49.3 degrees, which is just going to be 40.7. So we need to put that in a way that expresses it. We can say angle between the line and the plane, which is what we're actually asked for, is going to be a 90 minus our value that we've worked out, which is 40.7 degrees to 1 decimal place. Okay, so that's how we calculate the angle between a line and a plane. It's just got that little extra small calculation at the end because the angle that we get from our formula isn't the actual answer we're looking for. Okay, so hope that makes sense. That's all three examples done. You can go on and practice a few different combinations, and then we'll have a wee look later on at proving the lines intersect and finding the points of intersection of lines and planes, which is slightly different again. Okay.